Excitation contraction coupling is the marriage of an electrical signal that will be converted to a chemical signal that's going to stimulate contraction. In this case, we have an electrical zap, an action potential that's going to come down the length of the axon. It'll open up calcium channels at the axon terminal. Calcium will rush in. That tells the axon terminal, bundle up your ACH into vesicles. The vesicles will then be exocytosed, or the contents will be released into the synaptic cleft, and they'll bind to sodium-potassium channels that are on the other side of the synaptic cleft on the sarcolemma. Those ACH receptors are attached to sodium-potassium channels, and when ACH binds to a sodium-potassium channel, they open, rushing lots of superpositive sodium in and a little bit of less positive potassium out. Because the cell was doing work to keep the inside, relatively speaking, more negative than the outside, bringing a bunch of positive stuff to the inside is going to make the inside less negative. Therefore, the polarization of positive, the gradient of positives versus negatives on the outside versus the inside of the cell is less steep than it was before. It has depolarized. It's less polarized. Depolarization events at the end plate potential are going to stimulate adjacent channels to depolarize, which will stimulate adjacent channels to depolarize, which will stimulate adjacent channels to depolarize. As the signal jumps to the next set of channels, the upstream channel will close itself to depolarization and start the process of pumping ions back to where they started so that it can be stimulated to transmit the signal again. Now remember back to the microscopic anatomy of the muscle fiber, you have these transverse tubules, these T-tubules, that are invaginations of the sarcolemma. The sarcolemma is what that electrical signal is traveling through. So as the electrical signal travels along the sarcolemma, it's going to go down into these T-tubules. Adjacent to the T-tubules, you have your terminal cisterns of the sarcoplasmic reticulum. Remember the triad? Two terminal cisterns of the sarcoplasmic reticulum and a T-tubule makes a triad. So you have this T-tubule sandwiched by the terminal cisterns of the sarcoplasmic reticulum, and as it turns out, they hold on to calcium. They store a lot of calcium. And as that electrical zap gets transmitted down the sarcolemma, which includes the edge, the walls of the T-tubules, it's going to open up voltage-sensitive receptors that are in the sarcoplasmic reticulum adjacent to the T-tubule that are specific to calcium. So you store a bunch of calcium in the terminal cistern, and now you've just sent an electrical zap down the length of the T-tubule that opens up calcium channels in the sarcoplasmic reticulum. And this is going to allow calcium to flow into the cytosol and into the myofibrils to participate in contraction. Remember that calcium is going to act on the troponin of the light chain. It's going to then cause it to shift away. It'll basically make it change shape. It'll push the tropomyosin away, and the actin binding sites are exposed. So you send an electrical signal down the length of the axon that stimulates a chemical shift to happen. You have neurotransmitter bundled and then released. They bind to the sarcolemma. They bind enough to the sarcolemma and enough ion shift that you create an electrical zap. Zap. When that reaches the part of the T-tubule that's adjacent to the sarcoplasmic reticulum, that zap is going to stimulate calcium channels to open and let calcium rush in and then participate in the first steps, the first necessary steps for muscle contraction to happen at a molecular level. So this slide just looks at that last part of the process a little more closely. The sarcoplasmic reticulum has calcium gates that are stimulated to open by voltage changes only, by electrical shifts going on only. When they open, calcium rushes into the inside of the cell. Remember, the sarcoplasmic reticulum wraps around the myofibrils, and the T-tubules also wrap around the myofibrils. So the calcium is going to rush in, and then they'll bind to troponin. It's just nearby, so they're going to spontaneously bind. You have enough calcium released into that area, calcium's bound to bind, to bump into a troponin. And when two of those bump into a troponin, it stimulates the troponin to change shape, which pushes the tropomyosin out of the way of the actin binding sites. Now the actin binding sites are capable of participating with the myosin heads for contraction. While all this is happening, while you have all the electrical zappy stuff and ion shifty stuff happening, you also, inside of the cell, are creating a bunch of ATP all the time. You have all those mitochondria, you've got all those glycosomes, you've got all that myoglobin, you've got a bunch of just free sugars in there. You're constantly making ATP. Now remember, the steps of the power stroke. The myosin head is bound by ATP. It'll hydrolyze into ADP and a phosphate, and it'll pull the myosin head down into a cocked position, ready to go. So you start off with ATP. It'll cock and get ready to go. Oops, sorry, I circled the wrong thing. The actin head is exposed because of the calcium that's been rushed in. And so because the actin binding site is exposed and the myosin head is cocked and ready to go, and they're close to each other, they're just going to spontaneously bind. They're attracted to one another like magnets, kind of. So they're going to spontaneously bind because they're both exposed and they're next to each other. When the ADP and the phosphate ion are released, the myosin head is going to change position and pull forward. And since it's bound to the actin binding sites, it's going to pull that actin strand along with it. This is going to shorten the distance between the two actin fibers and shorten the distance ultimately between the Z discs. It'll shorten your sarcomere. When a new ATP binds, the myosin head is released and stages it to be cocked and ready to go again. This process, coupled with the excitation contraction coupling process with calcium release, is ultimately what causes contraction at a molecular level.